still dusty. This is Bloodhound, fresh back from South Africa where it did 628 miles an hour during its warm-up. But you don't want me telling you about it. Let me go and grab Andy Green. Right, Andy, first question. This car did 0 to 628 miles an hour in 50 seconds. Talk me through a run.
Mid-November last year, we're on the Hack Scheme Pan, and it's 8:30 in the morning. We've just been cleared to run, jet engines running. I've got 10 miles of track in front of me. It's time to try and do 600 miles an hour in Bloodhound. Left foot off the brake, right foot easing it forward to the detent for maximum dry power, spin the turbine up. Immediately the car leaps forward, stabilise at max dry just for about 1 second. As soon as I see that starting to stabilise, we're only doing about 30 miles an hour at this stage, push through the detent, straight up to max reheat. Reheat lights, the nozzle expands at the back, flames come out of the back, the car is now leaping forward at over 1G, 20 miles an hour per second. So we're doing the equivalent of 0 to 60 in 3 seconds, and it just keeps going at that speed, up through 150. Half a mile into the run, there's an old road that crosses our track, and going across that, half a mile in, we're already doing 180 miles an hour. The car is still accelerating at 20 miles an hour per second, up through 200, 220, 240, 260, and it just keeps going at that rate. Next checkpoint is 3 miles in. The old causeway we've graded off is a colour change, so I can see that very, very clearly. 3 miles into the run, the car is doing 500 miles an hour and still accelerating. Just a little bit of drag coming in now, so the drag, the acceleration is now down to dropping below 15 miles an hour per second, gradually down towards 10 miles an hour per second as we squeeze up towards 600 miles an hour. A little bit of a gusting crosswind from the right, so the car is moving around a little bit. I can feel it being pushed to one side and weathercocking into wind, so let it move, and as it weathercocks, a snap of steering on a couple of occasions just to keep it straight, keep it on the line, up through 600 miles an hour. Of course, we're in South Africa. The kilometre marks are the way we measure the track out there. So we get to kilometre 7, I hear the radio call for kilometre 7, we're just below 600. I know we've got about half a kilometre spare, so I'm going to give an extra 2-second count after that call, 1002, 1003, and then lift at 600 miles an hour indicated. Turns out the speedo was under reading very slightly, we're actually doing about 620 at this stage. Peak is at 628 as the jet engine winds down, and immediately I'm now starting to throw forwards in the straps because we're now slowing down at close to 1G with the aerodynamic drag. Immediately stabilise the car, still a little bit of a gust of crosswind from the right, so stabilising it, now steering it with one hand as my left hand drops down to the parachute lever, pull that at 590 miles an hour, bang as my head goes forward, an extra 1G of deceleration, an extra 6 tons of drag on the car. The car is now, in the next 4 seconds, will lose 100 miles an hour. 4 seconds from 590 to 490, then the drag starts to gradually tail off as the speed comes down through 450, 400, 350. It's all starting to move nice and slowly now, down below 350, looking for 300, and then 250 miles an hour. We're about a mile to the stop point. I can see the recovery crew. 250 miles an hour, we're now at slow speed, easing the brakes on, and anything below 250 is so slow I can pretty much get out and walk at this stage.
Right, Andy, let's start down the pointy end and you can talk me through the car. So, am I right in thinking this is titanium down the front?
Exactly right. This car was designed with the capability of going up to 1,000 miles an hour. Now, doing that in the thick air at ground level would generate a lot of heat, over 130 centigrade at the nose. Now, this is carbon fibre. That is plastic. We don't want to heat that up, otherwise it starts to get soft. So the metal nose tip is part of spreading that heat and protecting the carbon fibre. It is also, as it happens, 3D printed titanium nose cone, and that is part of showing off, showcasing the magical technology that's been built into this amazing car.
Fantastic. Right, let's move straight back up because this has caught my eye. There's a hole here with a number 52 by it. And there's another one here, and what are these about?
Absolutely. They run in a centre line up the car, and there's another whole bunch underneath the car. There is a total of 159 of these holes all over the car. They are pressure sensors.
Yeah.
The critical thing about taking this car to supersonic speeds is understanding and managing the enormous aerodynamic loads. Again, talking about the peak speed of 1,000 miles an hour, the aerodynamic loads then become something like 11.8 tons per square metre of what's called stagnation pressure. You know, the pressure you stick your hand out of the window
windows, yeah.
At motorway speeds. Well, if you do it at 1,000 miles an hour, your hand will finish up with a load of 1/4 of a tonne on it.
So thinking about the aerodynamics, because this surprised me a bit, You've got obviously loads and loads of screws where all the panels are connected, but they're not covered. They could disturb the airflow. Is that all right, or how is that meant to be?
It's absolutely fine. We could produce a little bit less drag and a slightly smoother airflow by taping those over, but that would be a fairly time-consuming process, and we would gain almost nothing, because they're slightly recessed, and as the air flows over the car, you finish up with a very thin, what's called boundary layer. So it's a very thin layer of near stagnant air across the surface. They sit underneath the boundary layer. It has almost no effect.
Right, Andy, there are some bits I recognise here, because there's a big spring and what looks like a conventional brake disc. So you've got some, what I recognise as bits of a normal car here. What are they doing for you?
It is pretty much exactly like you would recognise in a race car. I mean, if you think Formula One with a sort of, the double wishbone and pull rod, it's exactly the same here, except beefier. So you've seen the massive spring and damper
Yes.
unit there. The double wishbone and pull rod are actually buried in here. And to give you some idea, the pull rod in a Formula One car, you could put about a ton of load on it. So you could use one of those rods to pick up the whole car.
Yeah.
Ours will take 16 tons of load, so you could use one of those to pick up the whole grid. But we don't need very powerful brakes for this. Most of the braking is done with air brakes. These are just for driving around at slow speed and stopping the car from slow speeds.
But your version of slow speed
Slow
is...
speed, 250 miles an hour.
Yes, quite.
Race cars have carbon discs. Road cars have iron discs. We have steel. Nobody uses steel. The reason we've chosen that, the carbon, because the spin speed up at 8, 9,000, 10,000 revolutions a minute, the iron will have exploded a long time ago. The carbon, you are getting right up to the limiting strength of what that's capable of taking. The steel is strong enough to take those rotational loads.
Moving on, this has intrigued me. This cannot have been part of the original design. It's a water bottle with a pipe going into it.
Anybody that's been involved in motorsport knows that rapid prototyping is an essential part of the process. This is an in-field modification. This here is the cooling tank that actually absorbs all the heat from the jet engine gearbox. It was pushing out more heat than we expected and actually getting hotter than we expected. So although we had a blow-off valve here, we actually decided to fit an expansion tank just in case we did finish up with any fluid. So rather than it dripping out to the fuselage, we actually fitted this as an expansion tank just in case we finished up with any extra fluid. The right size of container we happen to have, the Bloodhound water bottle, available on our website, obviously, but the guys literally just plumbed it in overnight to actually make sure that if we did finish up heating this tank up, that's where the fluid would go. Behind the water tank, which will absorb a lot of energy itself, we then have the ballistic matting. That will then basically stop pretty much anything that the wheel could throw off. And behind that, of course, is the carbon fibre monocoque, which is the structural heart of the car, inside of which I'm sat. So I'm incredibly well protected behind all of this.
And did you have to take that into a ballistics laboratory and fire stuff at it before it was fitted to the car? Or did you know what it was going to do already?
That's exactly what we did. We actually fired a representative chunk of a piece of stone or a piece of aluminium that could come off the wheel at supersonic speeds and fired it at the appropriate angle into that stuff and proved it wouldn't go through. So we know this will work.
Dropping in, it's quite narrow, and Andy Green's about a yard taller than I am. Right, so Andy, what am I looking at here? I've got what looks like a 3D printed steering wheel in front of me.
Exactly right. A very conventional steering wheel, except of course it's not. It's 3D printed in titanium. It's another showcase piece of technology, but actually, Renishaw made that for us. It is made to the shape of my hand, so it's exactly the right grip with the buttons in exactly the right place. Absolutely perfect.
Now, I think there's a lovely story, isn't there, about the triggers you're using on the back of the steering wheel, in that they literally are bits from a drill.
Absolutely. Although we've got the most sophisticated steering wheel in terms of being 3D printed in titanium, pretty much the most sophisticated steering wheel ever, the switches just need to be simple and robust and vibration proof and dust proof. And where are you going to find those? You're going to find them in a builder's merchant. So the guys literally said, go down to B&Q, try all of the drills, see which one you like the feel of. And I tried them all. They looked at me a bit weird as I'm going around trying all these triggers. Black & Decker works for me. So they ordered a couple out of the catalogue, and that's where they came from. Then in front of your feet, you've got the throttle pedal for the world's most advanced military jet fighter engine, which sits behind your head. That's under your right foot, and under your left foot is the brake pedal for the front wheel brakes, those steel discs. And the very simple logic for the cockpit is that down the right-hand side of the cockpit is all the stuff involved in making the car go. So all the switches down the right involved in the jet, the rocket, etc., controlling all the power systems, and the left-hand screen is all about stopping, so brake pressures and the control systems, electrics, and all the switches that control things like the brakes, the electrics, the hydraulics are on the left, and of course the parachute buttons on the left-hand side of the steering wheel.
Those are the parachute levers, I guess, left and right.
The levers on the left are for the parachutes. Please don't pull those because the parachutes are live at the back.
Yeah. Okay, right, before I touch and disturb anything else, I think I'd better get out of here. Right, we've got this huge air intake. Two questions. One, why is it the shape it is? And B, if it was bigger, wouldn't you get more air in?
To take those in reverse order, if it was bigger, yes, we could put more air in there, but of course, what we need is not maximum thrust off the line. Very cool though it is to pull away with a massive drags to start. Actually, this is pretty quick off the line anyway. More importantly, we need maximum thrust where we've got maximum drag at supersonic speeds. So this intake is designed to capture exactly the right amount of air at 800 miles an hour, so Mach 1.1. So it's sized for the air tearing in here at 800 miles an hour to be exactly what the jet engine needs. It's a little bit small below that, it's a little bit big above that, but it's optimised for that speed to give us maximum power right at that point where we need it. The reason for the shape here is that we're using the cockpit is actually shaped as an intake ramp. So there are a series of complex shock waves at supersonic speeds which actually decelerate the air down to, you know, it's doing 1,000 miles an hour out here and it's doing 500 miles an hour when it gets down to here. So it's a huge deceleration of air to go down the intake because jet engines must have compressed subsonic air getting to them.
And is this a polycarbonate windscreen?
Yes, it is. It's actually a double layer. It's the same thickness, give or take a millimetre, as is used in the Eurofighter Typhoon. It's actually two layers bonded together, and that gives it a phenomenal strength. I mean, this will take a kilo of bird at 1,000 miles an hour, and it will basically bounce off. Now, that won't do the rest of the car any good because it will bounce off and go straight down the jet engine. So there'll be a loud bang at that stage. But nonetheless, in terms of protecting me from pretty much anything that the desert could throw at us, literally, this has been modelled to the same standard as the very best jet fighters in the world.
Now, the other thing that strikes me here is I can't see the engine. I can see an intake. How far down is it before you get to the engine?
The intake tube itself is actually quite long. It starts off in this strange upside down mouth shape and gradually turns to a round shape way back down here where it actually then joins onto the front of the engine. I'll show you where it is.
Let's go and have a look. Right, so if we work down the side of the car, well, first of all, what's this? It looks like a cooling duct.
It's exactly that. We've got cooling ducts down both sides. They actually put cooling air into the bottom end of the engine bay.
Fantastic. But we're not at the start of the engine yet,
Not yet.
So
got a fair way to go yet.
How far have we got to get before we get to...
A bit further. It's actually behind the fin intake. We're about there.
About here somewhere?
Front of the jet engine's about there. It's a very short, very compact, very powerful jet engine. Big long intake, and all of the power's made at the back of the car.
Wow. Does that have anything? Does that affect the the weight distribution of the car, and B, how it might pitch or dive under acceleration, for instance?
Great questions, and it was one of the key things that we spent a lot of time looking at early in the design. The initial thought was jet engine's going to be the heaviest single component in the car. It's got to go at the bottom, obviously. Keep the centre of gravity nice down low. The problems involved with that. First of all, it's the bulkiest bit of the car, so it's now left you almost no room for the rear suspension. And also the fact you were taking the intake at the top end of the car and having to bend it down through a big S-bend to get down to the jet engine at the bottom. The other problem with that is you then finish up mounting the rocket on top of it, and although the jet engine runs continuously pretty much throughout the run, when you then are running along the ground and you fire the rocket sitting at the top, it kicks the tail up quite dramatically, and when you stop firing it, the tail, there's a whole bunch of pitching there, which is less than desirable at supersonic speeds. It was one of our senior design engineers that said, let's just have a look at do the unthinkable and put the heavy bit at the top. So swap them around. Centre of gravity, first of all, has that. It moves it up about that much. So we'd like to have it lower, but let's look at all the positives. You've now got a straight through run for the intake, which is all good. You avoid making a hole in the structural centre of the car, so you don't have to worry about running the intake through, which is all good. So the rocket is now sitting in a line just underneath the centre of gravity. So now running at high speed, fire the rocket, it makes the back end squat down very slightly, which is good. And more importantly, when we stop firing it, there's a very slight release on the back end, but it's not significant. It's a much smaller pitching, so we don't get anywhere near the disturbances firing and then shutting down the rocket with it this way round.
Right, so engine's in here, air brake. Why has it got all the holes in it?
Yeah, very good question. If you take just a solid lump of carbon and push it out, you'll generate a lot of load, which is good because it's designed to slow the car down. But you'll also finish up with, as the air breaks away around the back end, you'll finish up with these huge vortices being shed. It will be quite violent and unstable action, so you'll get big fluctuations in the airflow around the air brake, and more importantly, everything downstream of the air brake, which includes the rear wheels and suspension. There will be an awful lot of buffet, there'll be some massive load changes down at the back end of the car, which we want to avoid. Drill a whole bunch of holes, you finish up with, instead of one huge great vortex creating all the drag from the air brake, you finish up with lots of little ones, each one of which is not very energetic, and they tend to interfere with and cancel each other out.
This little piece of metal, I understand, used to sit here and was a flat piece of metal, but it was the dust and airflow at 450 miles an hour that bent a piece of steel into that. How does that work?
It's actually slightly worse than you think. The first bits we bent were actually titanium. They weren't designed to be damaged, and they weren't designed to be disposable, but it turned out that they were just taking such a battering. What's actually happening, if you look all the way down the car to where the front wheel is, way up there, the front wheel is throwing up a spray of clay and dust and silt and fine sand particles, and they are tearing back down in the 500 plus mile an hour airflow, coming back down the fuselage, and it's being thrown up just high enough to kiss the bottom end of the bodywork. Now, underneath the bodywork, it eroded the paint away as a result, but that's fine. It's just skimming the bodywork. Then it comes to a sudden stop in this corner. Now, aerodynamically sharp corners are never good. The sharp corner, however, works really well at supersonic speeds. It's designed for next year's car, but for this year's car, as the sand hits there, it then suddenly hammers into this corner and starts battering away at the metal. And that piece of metal used to sit there, and literally it just crumpled all that up. It's just the mass of the desert being thrown up into it at very high speeds.
And the whole run's only, what, 90 seconds long, so
exactly, it's a quick process, and it really surprised us just how powerful that was. We then looked at some very detailed aerodynamic modelling from Swansea University and said, can you look at 500 miles an hour airflow from the front wheels, where's it? And sure enough, they said it impacts right here. And you can actually see the dust trace here. It actually comes up the side of the bodywork, and it's very localised. Look at the pull rod, completely stripped of paint, and it's gone rusty on the journey back. Look at the wishbone just above it. Paint's completely untouched.
Yeah.
It's a very, very localised effect just on this little bit starting down here.
Okay, so the rear wheel, I'm guessing it's solid aluminium. Tell me more.
Otto Fuchs forged a 250 kilo block of aluminium at just under 400 centigrade to a massive grade, what they call cheese. It's just like a huge cheese. It was then rushed by Top Gear, as it happens. The very first one was rushed from Germany all the way up to Glasgow to Castle Precision, where they started machining the first of the wheels, and machined it down to a 90 kilo piece of aluminium, which is designed ultimately to be able to rotate at over 10,000 revolutions a minute. And more scarily, at 10,000 revs a minute, that's 170 revolutions per second. This is the fastest wheel in the world by a long way. The wheel rim is pulling 50,000 times the force of gravity outwards.
Right, coming round to the business end of the jet engine, obviously, and I can see the fans down there. Where do you light it for the afterburner? Because obviously we saw all the cones of flame coming out. Where does the extra fuel get injected for that?
Well, the actual core of the engine is tiny. You know, the engine's only 4 meters long. The front half is all of the fans and stuff. The back half, the bit you're looking, is actually the flame holder for the reheat. So those fingers sitting back there is actually where the fuel flows in and catches fire to produce the flame pattern, which finishes up that massive great orange carrot sticking out the back, which is the reheated air coming out of the back end of the jet engine, basically just increasing the power of turbines running absolutely flat out already. It's going as fast as it can. To get more power out of that, you additionally heat, you burn after the engine, or the British term is to reheat the air by putting neat fuel in where those fingers are and just setting fire to it, creating even higher temperature, higher pressure, more thrust.
And how much more thrust?
It goes from around 6 tons of force, so 60 kilonewtons, all the way up to 90 kilonewtons. So it's a 50% increase
So it's
right
a big
there.
gain doing
Oh, yeah,
that.
it's
Yeah,
great.
That's the going. These are the parachute holders. You've got 2 of them.
Yeah.
But I think during most of the runs you were only using 1 of them. Is that right?
Yeah, exactly right. One parachute is more than enough to stop the car. In the same way that the jet engine produces an extra 60 kilonewtons of thrust dry, this will produce 60 kilonewtons of drag to slow the car down. So that's a 6-ton drag load in addition to the aerodynamic drag on the car.
Now, to come to the bit that's missing, which is this hole here. For next year, hopefully we'll have the rocket motor. Now, I just want you to talk me through the rocket motor, because I know the basics, but the figures sound so baffling. I want you to tell me about them.
The rocket is the most extraordinary, most simple device. I mean, just in terms of sheer size. Now, the rocket motor, the actual motor comes in 2 parts. The catalyst pack, which breaks down the hydrogen peroxide, and then the nozzle that actually directs the flow. So the catalyst pack is basically the same sort of size as this hole. It's about that thick, and then you get the nozzle spreading out, like a big sort of cone-shaped thing on the end, and the whole motor is only about this big, and about that much. Tiny, tiny bit of kit. Now, obviously, we've got pumps and the electric motor and the battery pack further up the car. The actual motor itself is being fed concentrated hydrogen peroxide, high test peroxide, and that's water with an extra oxygen atom bolted on, H2O2. Comes through these multiple layers of silver oxide catalyst. That breaks down the water. It splits the molecule to water and oxygen and a lot of energy. So it actually generates steam and oxygen at 600 centigrade. Feed it through this nozzle, and it accelerates the flow up to Mach 3. It's over 2,000 miles an hour. This jet E-Flex comes out.
In how much space? So it's going from nothing to that much.
It goes from liquid as it comes in here to Mach 3 steam and oxygen coming out of the other end.
In that much space?
In that much space. And that will give us, on a button press, pretty much instantaneously, an extra 6 tons of thrust on top of the 9 tons we've already got from the jet engine.
Right.
And that's the bit where the car takes off and goes.
Wow. So you were going to use a Formula 1 engine to pump, and originally you're going to use a Formula 1 engine to pump that fuel into the back of the catalyst pack. You're now going to use electric motors.
Exactly right. 12 years ago when we launched this car, I was very keen to use electric because there's all sorts of advantages. 12 years, awful long time in the electric car world. When you look at how Formula E's come on in the last decade, how hybrid and fully electric cars, the technology just didn't exist 12 years ago. Now it does, it's off the shelf. So we can get a 500 horsepower electric motor, and the battery pack, it's basically the sort of size of an airline carry-on bag, can give you enough power to run that motor at 500 horsepower for 25 seconds to pump the ton of hydrogen peroxide through that rocket motor that will give us all that extra thrust. And the astonishing thing, as I found out, you can then recharge that battery in about a minute. You can feed the power back in as fast as you take it out. It's extraordinary. So all of a sudden the turnaround starts to look really, really simple. And more importantly, we are using next generation space launch technology. We are using very much cutting edge and next generation automotive technology in an end-to-end zero emissions green rocket system that takes electricity and hydrogen peroxide and fires out steam and oxygen into the atmosphere at the other end and generates 6 tons of thrust doing it. What's not to like?